All right, great. Thank you. All right, so good morning, everybody. Welcome to my corner of the laboratory here that we do a lot of the magic that happens before the active treatment system gets put onto a project. My name is Vernon Slater. I have 14 years of experience in the field. My qualifications, I'm an active treatment system operator and trainer. I have a degree in chemistry, the CPESC, Certified Professional Erosion and Sediment Control, Qualified Stormwater Practitioner, and Qualified Stormwater Developer, and then a QUIS, a Qualified Industrial Stormwater Practitioner. So the position that I have in the community is I'm a project scientist for an active treatment system. I mean, I do a lot of design and testing to determine what's going to happen out there in the field. I brought this morning with me Spencer Davis. He will give a little rundown of himself.
Hi, I'm the manager of technical projects and lead estimator here at Active Treatment Systems. I'm a qualified stormwater practitioner, and I will soon be a qualified stormwater developer. I'm working on my CPESC. So that's what I do here.
All right. And so what I did is I've got a lot of frequently asked questions from various parts of the stormwater community, and I organized them in sections where the info is going to be similar. And when I start out, I'm going to kind of start with some of the entry level stuff. But if you're really beyond that, hang with us because we're going to be moving on to information about system sizing, some calculations, base and design recommendations, jar, dose testing, and jar testing, dose determination. So hang with us and we will get to that kind of stuff. So one of the initial questions I still receive all the time is, why is there a need for an active treatment system? I never had to have one before. And so I have a few facts here that come along with this. So 1/8 of an inch of soil from 1 acre is about 25 tons of sediment deposited into local lakes, rivers, and oceans. So the way to think about this is a yard is about 2,000 pounds or a ton. So take your 25-ton yard dump truck, pull it up to the normal local creek and dump it. And that's what you've done with 1/8 of an inch of soil washed off of 1 acre. Also, excessive turbidity or suspended solids absorbs more solar energy, raising the water temperatures. So I did a little research on that, and the current models show by the year 2020, all ocean ecosystems will have been changed by temperature increases as well as pH. Many fish populations will not survive that. So unless we do something now. Again, large amounts of suspended solids or clays may clog the gills of fish and kill them directly. Excessive turbidity may bury and kill eggs laid in local rivers and lakes. High turbidity blocks out light penetration that other beneficial plants and organisms need to grow. High turbidity promotes algae growth. And then when the algae die off, they consume dissolved oxygen, which can cause fish kills. The turbidity negatively affects aesthetic qualities for recreational uses. And then municipalities that have to deal with this water is negatively impacted. So I'm going to start sharing my screen a little bit here. And why am I not seeing what I want? There we are. It's letting me pick. There we go. So this is a picture a lot of people may have seen before. It's an example of a BMP failure, a big failure. BMPs do fail. And when that happens, we end up with water that's running off of sites, maybe getting into storm drains like we see here. And then you have the combination of that dirty water running into clean water. And I'd like to note here that that clean water is traveling for miles and a lot of acreage of runoff through naturally covered with natural vegetation. Then off of a small site, you get this dirty water coming from just a few acres because it wasn't managed well. And then so ATSY, here's another sample. So this is without treatment. This is with treatment. And this with treatment can happen within a few minutes. Same thing here, another example, very easy to see with treatment, without treatment. And then what we end up with is guys like this that are very unhappy living in their environment. These otters, they are genetically designed to be able to capture prey in very turbid waters, but it becomes more difficult when it's very turbid. And then you end up with guys like this that if that fish is probably living in around 500 NTU water there, if we raise that anymore, that fish will die. And then what about regulations? So direct violations of the Clear Water Act result in fines starting at $3,000, and they rise very quickly from there. And then there's lawsuits brought about by environmental groups. So eyes are everywhere. You have to be ready. So my next question that I was received a lot is, what is turbidity and why does turbid water remain dirty over extended periods of time? So turbidity is a general term used to describe the cloudiness or dirtiness of water like this around the fish. So it gives a numeric value to determine how bad the water is. The turbidity of any given sample is determined by passing a light through a sample, measuring the reflected scattered light, and then it uses that to determine numbers of nephelometric turbidity units, or NTUs. Turbidity is a good measurement of a water body's health. And then turbidity range for construction discharge. Right now, it's at 250 NTU max with just BMPs. The new permit coming out is stating similar value. But when you're using an active treatment system, because they can produce very clean water, those turbidity values drop to a 10 NTU daily weighted flow average and 20 NTU out of any maximum out of any single sample. So now the primary factors why water stays dirty over extended periods of time. So here we have very small, fine suspended sediment particles with repelling negative charge. That is the primary mechanism that is keeping your water dirty for extended periods of time. This negative charge repelling one another. They don't want to come together to form a larger product that will settle. And the second problem with why they stay suspended is particle size. So the very fine suspended sediment, usually 0.02 millimeters or smaller, just will not settle because the water will displace that particle size and will not allow it to settle. So next question was, what is pH and what does it have to do with stormwater treatment? So pH is a measure of a water's sample's acidity or basicity. So here's the pH scale from 0 to 14. The typically drinking water is around 7, sometimes as high as 8 or a little bit under 7. Notice here where it says healthy lake at about 6. Discharges for stormwater 6.5 to 8.5. This particular range is good for lakes. This is just an extremely healthy lake representation. Different treatment technologies may require different pH ranges for effective contaminant removal. So for example, a popular coagulant used in treating construction stormwater runoff is known as chitosan acetate. Effective pH range for this polymer is lower than 9 and above 5. At a pH of 10, the polymer just doesn't really do the job. So to raise a low pH condition, we add a base such as sodium bicarbonate. Stronger chemicals can be used like sodium hydroxide, potassium hydroxide, things like that, but you have to consider cost, safety, handling, and application to evaluate all of that before you decide to use those things. Sodium bicarbonate is preferred because its pH, see here, baking soda, that's sodium bicarbonate, is 9. It is very hard for me to add enough baking soda to low pH water to raise it above 8.5. I prefer to use this. To lower a high pH condition, an acid such as carbon dioxide or dry ice can be applied. Also, stronger chemicals such as muriatic acid, sulfuric acid could be used, but again, safety, handling, application all have to be considered. In this case, dry ice or CO2 is a preferred chemical due to the safety factors and ease of application. And the same thing with sodium bicarbonate. CO2 has a hard time pushing the pH below 6.5. While it can do it, just like sodium bicarb can push the pH above 8.5, you have to really try hard to do that. Next question, what is an active treatment system? So any treatment system that uses a chemical to reduce and remove fine suspended solids from construction site stormwater discharges. In other words, any system that's going to use a chemical to remove fine suspended sediment. A typical system will be made up of these kinds of, you have some pumping, some monitoring, some pre-treatment, and notice depending on jar tests, so that's going to be your pre-treatment. You're going to do jar testing. And then you're going to have some mixing, coagulation, flocculation, settling, pumping, monitoring again to make sure, and then a little bit of chitosan to be added just as a polishing chemical to the sand filter to make sure everything comes out very clean, and then filtration, monitoring, and discharge. Here is a representation of a very large system where water comes into the main basin this way, comes out, is pre-treated, comes over to the basin here, comes out of the basin, comes over, it's analyzed to see if it's ready to go to filters. If it is, it's slightly treated, goes to filtration, comes out of filtration, and goes to either discharge if it's ready and it's meets specifications. If it's not, it goes back to recirculation and gets retreated until it is ready. An active treatment system is portable, temporary, small wastewater treatment system that generally treats from 200 gallons per minute to over 1 million gallons per day, which is about 700 gallons a minute, 24 hours a day. An active treatment system protects natural waterways from the negative consequences of construction, land disturbances, or other man-made water quality problems. The active treatment system is the BMP of last resort. When when traditional BMPs may not control the accelerated release of sediment from erosion caused during rain events. Used where highly erosive soils are present, long steep slopes, clay and colloidal clays are present, or very, very large sites where you're going to, the sheer volume of water BMPs are not going to handle. Now, I had an interesting question come in a couple of days ago, is what is the difference between an active treatment system and a dewatering system? And a lot of these questions are starting to occur because of Department of Transportation, and there's some confusion when they call out an active treatment system and they're actually using a dewatering system. So the difference is an active treatment system use chemical reactions to remove contaminants from water. The ATS must meet chemical residual requirements in the discharge, and the active treatment system will always use chemicals in the treatment process. Dewatering systems, on the other hand, are generally systems designed to remove contaminants by way of mechanical means. These systems differ from active treatment because they will use settling, mechanical filtration, and specialty medias in place of chemicals. At times, the turbidity level of the water flowing to the dewatering system may need removal before specialty media or to meet local discharge requirements. In that case, the dewatering system will become active in the fact that chemicals will be applied to reduce suspended solids. In this case, residual requirements will need to be met. So effluent monitoring requirements change with dewatering systems. So typically, the dewatering system will be run in recirculation, then sampled to see that discharge requirements are met. After verification, the system will then be monitored on a periodic schedule developed for that discharge location. And that's provided you're not using chemicals. If you're using chemicals to remove that fine suspended sediment, you will be doing daily residual tests. But if you're just running a dewatering system through a media, once you've guaranteed it's working, then it only has to be checked on a periodic basis. So how does an active treatment system clean and correct pH of construction stormwater runoff? Active treatment systems use chemicals, sedimentation, and filtration to correct turbidity construction runoff. Turbidity is removed using cationic polymers and flocculants. And I almost forgot. I had a couple more pictures to show you what active treatment systems look like. I was wondering where that picture came from. And here we see tanks, the control system, filters. Here we've got our control system with the filter inside, tanks, and the generator ready to run the water. So now back to use chemicals and sedimentation to filtration to correct turbidity runoff. So turbidity is removed using cationic polymers and flocculants. So we add a positive charge cationic coagulant, neutralizes the electrostatic negative charge, and these very fine suspended sediment particles become pin floc. And this is the coagulation step. Now next comes flocculation. The chemicals bind with anionic suspended solids, causing them to combine into larger masses that will gravity settle out of solution. So water chemistry. So now that we've added more cationic polymer if it acts as a flocculant, or we have to add a flocculant to bring everything together into the large enough masses that we can remove them by filtration or gravity settling. After some operational time, the trapped particulate will begin to clog the sand filters and backwashing will become necessary. This process reverses flow through the filter and out separate plumbing back into the headworks or into a designated backwash tank. All right, so dirty water is collected where some of the heavy settle out and sand, and then this water is bench tested to find the best starting dose. With the dose known, the water is pre-treated using a static mixer. This is a photo here of a type of static mixer. So essentially, you end up with your polymer mixed 100% through this tube. Here's another style. You get 100% mixing, and very good diagrams showing you what's going on here. The water folds on itself. Now the pre-treated water flows through a tank or a basin. Here's a tank. And so the pre-treated water flows in, settles, is forced under a underweir. The settled water stays down, the sediment stays down. The clean water comes up over an overweir and out to filtration or to local sanitary sewer, depending on the system setup. In our case, active treatment systems, we'd be using filtration at that point. In a typical one season small systems, 200 to 800 gallons per minute or less, treatment will usually be done in tanks as water, and then in basins. Basin design is the utmost importance. 90 minutes of contact time and basin design feature will need to be met. When designing basins, perfectly round basins like you see in clarifiers are not helping us. They have issues of short circuiting. So I've got a couple of pictures, some basic hand-drawn photographs of basin shapes. So use a oval. You can put a weir wall across here, lower than the total height of the pond, and collect clear water out of here. The same thing with a rectangle, or if you're going to make a round pond, put a weir wall across here. We will run plumbing across here that will spread the distribution of the water into the pond so it flows equally all the way across. The thing to avoid is this: no weir wall and round. So as water flows into here and I pump it, it begins to flow straight across. It short circuits all of this. It short circuits all of this. None of this is really used for settling. You've wasted space on your site making a pond that doesn't work very well. Water is then pumped from the overweir side of the opposite end of the pond, usually about at 100 NTU water clarity, and then the water is filtered. And so here's filters shown. Here's the backwash shown. So reverse the flow. The influent water is still coming through into the filter like it did here, coming into both filters and coming out the bottom to discharge. Here, we're coming into one filter. We've opened a three-way valve here, so water cannot flow into it. It can only flow out through the backwash. Part of the water will go to discharge, and part will be used to push the backwash flock out. So when you do this, with ATS systems, active treatment systems, certain California Regional Water Board requirements must be met before discharge, including discharge turbidity requirements, 10 NTU and 20 NTU, pH requirements, right now 6.5 to 8.5, automatic logging of water quality parameters, training requirements, chemical residual requirements. All right, and then I had an additional question. It was, and how does pH corrected with stormwater? It's using three methods. One, we'll sparge gas into the waste stream through an injection quill and a static mixer. We can add pH correction chemical to the tanks or ponds by hand, or we can add chemical injection into a static mixer. That's the three methods to correct in pH. So what types of equipment are used in an active treatment system? We have process pumps and chemical pumps. So here's some process pump examples sitting out on a floating platforms here, centrifugal pumps sitting up on the bank. You can also have diesel pumps. Total dynamic head is important to understand. So if you're using a pre-treat pump, TDH is fairly low. You're just transferring water from one location to the other. Where when you're putting it through a filter, you need high total dynamic head to be able to force water through the filter. There is your chemical metering pumps with our calibration cylinders below. We have some tanks here and basins, and notice the oval shape here. And notice here that the contractor, when they were building the basin, made one error. We put pumps here, they put the influent here. The ideal situation here was the influent would be here, the water would flow across with settling to the pumps. So a slight error made here, but it was workable because of the second pond. Valves, you got some automatic valves. You got a fail-safe open, fail-safe closed. Both are used on active treatment systems. You have your manual valves. These are also known as throttle valves. I can control pressures and flow rates using these. And then some instrumentation. We got these turbidimeters, pH meters, flow meters, and filters. Now I'm going to lower this size a little bit for the next pictures coming through. So water system footprint requirements. So a typical 200 gallon per minute system with one tank, that's using a 20-foot container and a standard size filter, will need to be about 800 square feet. And the shape of the pod will be based on site constraints, but we'll need room for a tank that's 40 feet long and 10 feet wide. And now here is a system showing a rectangle pond. Influent would be over in here. Effluent would come out of here. We're traveling through our control unit to be pre-treated, coming out, pumped, go to filters, and so on in the system. For each additional 200 gallons per minute added, expect about 400 more square feet in the shape of a 40-foot by 10-foot tank. So again, the only thing that changed here is one tank and another tank for 800 full gallons. These constraints will follow suit up to about 800 gallons per minute, and at times can squeak by 1,000 gallons per minute. When the systems are larger than 1,000 gallons per minute or are multi-year operations, basins rather than tanks really start to make sense. So I am going to break this back to 100% as I move on. How is system size determined? System size is determined by looking at overall, let's see, time. Okay, I'm good. Overall project overall project disturbed acreage and the rainfall that will occur at that site in the 10-year, 24-hour rain event. With the amount of rainfall known, available storage must be calculated. Then the system size is calculated to pump and store the volume equal to the 10-year, 24-hour rain event in 72 hours. This yields the minimum system size that California water boards will approve. However, backwash and equipment or system upsets must also be considered. Therefore, a recommended system size calculation would be 35-hour pump down. So where do you find your disturbed acreage and location? Right on your notice of intent. This is a copy of a notice of intent. And on the notice of intent, you will notice you have latitude and longitude, and you have size of the site plus disturbed acreage listed here. So in this case, they showed 260 acres in this latitude and longitude. Rainfall amount is found using the latitude and longitude and by going to NOAA 14-point precipitation frequency estimates. So this website, you type this in, and when it opens up, it's going to show you a map of the United States. You click on California. At the top of the map, it will have two fields to fill in, your latitude and longitude, and you will submit that. And then you will get a map like this and a chart showing rainfall based on duration, 5 minutes, 10 minutes, 24 hours, and years, 1 year, 2 year, 5 year, 10 years, so on. So this information, what you have to do is look at the 10-year, 24-hour rain event. So I've highlighted 10 years there. And I come down to the 24 hours, which give us a 3.88 inches. Now for the calculations. Now I use a 10-acre site. I used everything else as we found it, 3.88 inches, 10 acres times this factor, never changes. And you get a total gallons of 1,053,000 gallons. If you divide that by 72 hours and then 60 minutes, you get a system size of 244 gallons per minute system. That does not include backflush and does not give you a time for equipment breakdown or other mishaps that happen on a site. So use a 35-hour calculation. At 35 hours, the system size is this. You divide by 35, divide by 60 minutes, and you come up with a system size of 462 gallons per minute. Now, we know from looking at this already, we'd like to run about 200 gallons per minute through a tank. This 244 shows that we're going to need 2 tanks anyway. And this 462 is saying use 3 tanks. And 3 tanks does not make sense on this particular site for the volume of water. 2 tanks does. So lower this to 400 gallons per minute, run the numbers backwards and find out the hours of pump down. In this case, it's 42 hours. When you look at 42 hours and you say 72 hours, that's about a 30-hour break if needed to replace equipment or slow the system down because it becomes overloaded. Heavier storm comes in or different construction happens, disturbing different acreage that's causing us more problems. So that will give you the time to keep up with that. So that is how a system size is calculated. And you can do this for yourself and already have an idea of what your system size needs to be. Then you can call us up and say, I need a system about like this. What's it going to cost? All right. So now, what is chitosan acetate? Chitosan acetate is a non-toxic cationic biopolymer. It is made from chitin found naturally in crab shells. Its unique characteristics attract and bind with anionic solids and colloidal particles. Chitosan polymer starts out at about a pH of 4. This is a very crude drawing of a three-dimensional object. I'm doing it in 2-dimension here to give you an idea of what's going on. I think this is a very easy way to explain that. So we've got a tightly wound up molecule with all of its cationic sites kind of hidden at a pH of 4 or slightly less than 4. As the pH begins to rise to 5 or more, that polymer chain opens up and exposes all these cationic sites where anionic particles can now grab. And then at a pH of 10, what happens is this polymer becomes severed, for a lack of better words, and you can still get some coagulation particles here, 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 and here, but the flocculation will not occur, and you can keep adding polymer and it will not help. So chitosan is a pH sensitive and therefore needs to be used in pH ranges that are conducive to construction stormwater discharge requirements. When pH is 9 or above, chitosan will not work as well as 8.5. At pH 10, well, the molecule is severed and doesn't work. Speaking of chitosan, the question here, I've heard of chitosan referred to as a coagulant, flocculant, and polymer. Which is it? Chitosan is a cationic organic polyelectrolyte that is a polymer and behaves like a coagulant and a flocculant. So chitosan by itself will start the coagulation process and continue to form larger settleable masses without the addition of a flocculant. A lot of polymers and coagulants out there do not behave that way. What is the difference between a coagulant and a flocculant? That was asked for a couple of weeks ago. A coagulant is a substance that causes particles to clot or bind together. Typically, this is done using a coagulant of opposite charge of the target particle, like our case, cationic polymers attacking anionic particles. The flocculant is a substance added to a suspension of coagulated particles to form larger particles that can gravity settle or be removed in filtration. That is a big difference between a coagulant and a flocculant. Does chitosan work with truck wheel washes? And I've had this question come across in a couple ways, and in many cases, yes. However, there are pH limits. So truck wheel washes from a concrete plant where elevated pH would be expected, chitosan's not a good choice. When used on muddy sites where track out pH is 5 to 8.5, expect very good reaction from the chitosan. Recommended uses for chitosan and truck wheel washes would be systems like maybe a Moby Dick truck wheel wash with an automatic sludge removal. So that's constantly pulling out the sludge at the bottom. Or maybe in the morning, after the system is sat and not been used overnight, you'll have everything completely settled out, clear water with all your sludge at the bottom. You can bring in a vactor who can vac out just the bottom, saving most of your water and effectively removing the sludge, getting you primed and ready for the next week or day, however often you need to clean up your truck wheel wash. All right, so now comes down to, I'm going to stop sharing. And how is coagulant dose determined on any given water sample? So coagulant determinations happens in 2 places, one in the laboratory on a lab bench and then in the field inside a control unit. So for the lab bench I've got set up here, you grab 5 to 10 gallons of actual site water sample, or you produce simulated stormwater using distilled water and actual site soil samples. I've worked 14 years finding out what I needed to do to make simulated stormwater that is representative actual site conditions. You set 6 jars onto a 6-position jar test apparatus and 1 control sample on its own mixing apparatus. So you can see I have my control and my 6 position that's going to be treated with polymer. This one will not. Prepare different doses for each jar. So each of these injectors have a different dose. I'm going to go ahead and fill this one right now. This one I want to do, I've done 100, 150 parts per million, 250, 350, 450, and I'm going to do 550 in this. The polymer I have is a 10% mixture where 1 milliliter equals 100 parts per million. So I'm going to go up to 5.5 milliliters in this, and I'm going to set that up and get ready to inject. I'm going to need a little bit of deionized water. Give a little shake to make sure that's evenly mixed. Squirt out all the air. Take this down to 5.5. Now to make sure they all have the same volume, bring this up to 10. And there that is. Let me get this out of the way. This one takes a little longer to get up to speed than these other ones do, but this one gets there. Yeah, there it is. It's up to speed. Okay, so I pull the pins. I have my stopwatch, and I'm ready to inject. So for an actual active treatment system, this requires a very fast flash mix. You get a 30-second flash mix of high speed. You get 15 more seconds of half that speed and 15 seconds at 50 RPMs. And that represents what's happening because it takes about a minute to get from the static mixer into the tank. All right, there's half speed. Half again at that. And that is done. Now, Spencer, if you'd like to help me just lift this up and slide each one forward, it'll be a little easier for these guys to see. And I'm going to bring this up and give everybody just a see how fast. Where's my flashlight? I had my flashlight here. How fast this is happening and how clear that water is becoming. Now, what I would like to point out, this dose here was about 100 parts per million. 150, 250, 350, 450, 550. And as you can see, this one's still a little dirtier with more polymer. So more of a good thing is not better. What I have done and why this is remaining dirty is I have applied an excessive amount of a cationic polymer. So before, when we had suspended solids like we have in our control sample, these negative repelling charges are keeping each other from wanting to come together and settle. What's happening here is I've added enough cationic polymer, I've overdosed, and I've changed the solution in the water from an anionic repellent to a cationic repellent. So this water at 550 NTU would not be a good dose to start with. Now, out of these two, I got to test. What I need is about 100 NTU off the top of the water after 5 minutes of settling. If I get that 100 NTU, then I know that's a good dose. So while this may be a cleaner dose, if I'm using 100 parts per million less, that's about 100 gallons of polymer, or about $1,300 for every million gallons of water treated, less expensive. And it's possible when I'm operating a system that I would find the dose that'll be right between this one and this one, and even lower it some more, rather than just kind of shoot from the hip and just add plenty of a good thing. That will get the job done, but what do? We cost you more money. We risk putting polymer in the environment because we're using more than we should. So the negative consequences are, it's just not worth it. And so now I'm going to go ahead and take a couple of, some pipettes here. And I'm going to take a sample of water off of this one. And I should be wearing gloves right now, but I'm not. So I'm wiping all my fingerprints off of this to make sure I get good. Invert a couple times. All right, we're going to look for turbidity here and see what this one is. 62.9. I'm not sure if you can read that, but it's 62.9. That's a little low compared to what we need. So I'm going to go over with a different pipette, and I'm going to check the 100 parts per million, because that looks like a dose that I can filter and successfully discharge water in the specifications required by the board. Invert a couple times, place into my turbidimeter and see what we have there. 120. So if we're looking for 100, the dose is slightly between 100 parts per million and 150, and this could be dialed in the field. I could do more further testing by, right now, I'm using a 10% mixture I made this morning. If I made this 1%, then I could really go through these and figure out exactly what that best dose truly is. A lot of times this can be done in the field. Now, the other thing that I have to do on this, even though I've got an answer right now, the board has put in the requirements to follow a standard called ASTM D2035-08. And that requires me to do 3-3 repeatability. So what I have to do is I have to take my best dose and I have to repeat it with 2 doses of that, 2 doses of the dose below it, and 2 doses of the dose above it, and repeat the test to make sure it does exactly what I think it does. So that's the 3-3 repeatability that we also do. In the field, let's see what time I have there. So I'm right at 10. Okay. So in the field, imagine that you go out, it's pouring down rain. You've grabbed yourself a liter of water, you've got your rain gear on, you're trying not to drip in it, you're doing the best you can, and the only thing you really have is one of these pipettes that we know from weighing the mass of these drops 50 parts per million, 50 milligrams into this 1,000 milligrams here, or 1,000 grams. So I am just going to put 50 parts per million in there. I'm going to do some mixing. And then I'm going to get my handy flashlight. And I'm going to look in here. And I'm going to see, I see some coagulation going on, a lot of fine particulate, not the big flocculation that we saw coming in the jars on the jar test. So I already know I'm going to be using more polymer. All right. I'm going to mix again real good. This time I'm going to mix a little bit better because mixing, it's hard. A static mixer can do in 1 second what it would probably take me an hour to do of mixing time in this jar. So I can't quite mix like it can be done in reality. All right, now, whoa, look, bring this up a little bit closer and you can start seeing, hopefully you can see that, I'm trying to see it, some flock coming out and settling. And now that's 100 parts per million. And I would probably have to mix that again to get the real settling on the top here, just because it takes that much mixing to meet what happens at a static mixer or with my jar test mixer. So that's our field determinations. Now, what if my site is contaminated and regulated by other constituents such as metals, hydrocarbons, PFAS or polyfluoroalkyl substances, diesel, gas? The PFAS are becoming very, very important for us to deal with. They bioaccumulate. We need to get them out of the environment, and we can do that. So how do these media work? So carbon, excuse me, other media can be added to the treatment tank. These media are typically contaminant target specific. There are various carbon materials, clay materials, and various mixtures of these available. So here's a mixture of clay and carbon. Here's just the clay material by itself. And then I have carbon. And I'm going to try and pour some of this in my hand so you can see how light, and 1 gram of this has 1,000 square feet of, I think 1 gram has 1,000 square feet of surface area or something to that effect. It has a lot of surface area. And so the other considerations in granulated activated carbon, or GAC, is type being purchased. Oh yes, I wanted to mention this, acid wash carbon. So what I just showed you is acid wash carbon. If you choose to take a lower bid using non-acid washed carbon, to get it to be low, the pH ends up being high on the effluent. So if you recycle it and recirculate your water, your pH will come down. However, the whole time you're doing that, you're stripping the water of dissolved oxygen. So then you have a dissolved oxygen problem that you have to deal with. So purchasing GAC is very expensive, but purchasing it acid washed is the way to go. All right. Oh yes, here it is, 1,000. That's right. GAC has a surface area. So how does it work? 1 gram of material has about 1,000 square meters of surface area. Contaminants passing through this material are trapped and adsorbed by the GAC. Clay materials, zeolites, organoclays adsorb contaminants within their media. So a typical system may consist of a control unit, a sand filter, coagulant, cartridge bag filter, followed by specialty media of choice. The goal is to keep the media influence, so that specialty media, less than 10 NTU. With the chemical used involved with stormwater treatment, how do you guarantee no chemical is released into the environment? I am going to share the screen real quick. And where was I? There we go. And residual testing. So this shows what we do is we collect a liter of effluent. I have 2 liters of effluent. 1 liter you're going to spike with a known amount of chitosan, and 1 liter you're not going to do that. Then you're going to force that water through a glass fiber filter and apply iodine. And iodine reacts with chitosan. If it's dirty, you're going to see something like this. This will be your spike. And if your spike looks, your blank looks like this, then you have discharged chitosan and you have to stop your system and fix it first. Typically, this is what you're going to see on your discharge water. Each polymer must have a residual chemical test that yields results within 1 hour and tests to a specific level that's based on the chemical abuse. Which again is another reason why chitosan is like to be used in stormwater treatment, is you only have 1 residual test. If I had to put in a coagulant and a flocculant, I'd have 2 residual tests. I'd have to test for both of them. And then the testing level is 10% of the maximum allowable threshold concentration. That is determined by taking a population of fish for chitosan. The most sensitive species is rainbow trout. You look at the no effect concentration and the low effect concentration. You take the geometric mean of that, reduce it by, and that's your maximum allowable threshold concentration, reduce that down 10%, and that's what you can discharge at. It's got to meet that or less. So that's winding down to the end of my presentation that I had. I'm open for questions. If anybody had any particular questions they'd like to ask, I can do that now, or I will move on with kind of wrapping this up.
It looks like Mel has a question in the chat.
Okay.
It says, my BS is in chemical and environmental engineering. Does ATS have the capability to custom design ATS systems for any list of constituents we provide? Beside constituents, what else would you need to provide an estimate and concentrations, flow, volume? Just looking for minimum requirements to help facilitate creation of a state-issued contract.
Yes, in fact, that is what we would do. So what we would do is we'll put, find out the constituents of concern and their concentrations. Then we determine the correct media to be used to remove those constituents. And we put in the amount of media. So we determine approximate volumes of water that would be flow and the length of the term of the job. And so, all right, this many pounds of material there will guarantee that we will remove those constituents to a level that's dischargeable for the entirety of the job. That's how that is particularly done. Did you have any input on that?
Yeah, I mean, the main thing you want to give us in order to figure that out is your flow rates that you're expecting, duration of the project, where the project is located. Where the project is located will tell us whether the sanitary sewer is an option or what regional water board we're operating under, which will let us know the discharge limitations, which is important. Each regional water board has different permits that you have to follow. And then your constituents of concern and their levels. Those are the main things. The rest are just operational stuff, like equipment, forklifts, stuff like that. But those things will allow us to design a treatment system. And we can confirm some of that stuff in the laboratory.
I hope that answers his question.
Awesome. Well, we are about out of time. We have to jump off this call because we have a test meeting in between now and the Yosemite workshop. So if you want to see Yosemite live on Zoom, join back on our workshop at 10:30. You can click the link on our website and we will be live broadcasting from Yosemite. So the internet's a little spotty, so we have to do a test before.
Right. Can I quickly just kind of run through some of our contacts here real quick? Like
absolutely.
So I have Active Treatment Systems. This is my address. You can send me samples of water and soil. If you're not sure how to collect your soil sample, call me. I will tell you exactly what to do, and I can make a very representative sample of your site and determine what you need. This is our company's website. This is our phone number to our main office, so you can get a hold of anybody. This is my name. I'm the project scientist. This is my contact. Notice that it is our first letter, last name, and all this ATS-GNV is always the same. This is my contact phone number. Spencer Davis, you already met, same thing, S. Davis at 8. He's an estimator. There his phone number contact. We have another estimator named Demetrius Villasana. He's an estimator. This is his contact and phone number. And then 2 guys from sales. We have Chris Larson, sales representative. This is his contact and phone number. And then his sales territories. So typically what you're going to see from him is right here in green: Napa, Solano, Contra Costa, Alameda. And he's going to represent all of Southern California and out of state. And then we have RJ Reynolds. He's a sales representative as well. This is his contact and his phone number. And his sales areas include all the peninsula, this area in red, Monterey up to Sonoma, Marin, Santa Clara, all of Sacramento greater area, Placer, El Dorado, Sacramento, San Joaquin, Yolo, Colusa, Lake counties. That is his territories. And I believe, Rebecca, that is it. So that should leave you enough time to do your sample. And I sure appreciate you letting us do this today.
Perfect. Thank you so much for sharing. And thank you everyone for attending. We'll see you at the next workshop.
All right. Thank you.